Swayam Prabha. Digital India. Educated India.
Welcome everyone to another segment of supplementary videos. So in this video we will see an example of where we will be using the method of Lagrange multipliers that we discussed in the previous segment to a practical problem in statistical mechanics. Okay, so let's consider this problem. Okay, so the problem that we have in our mind is, so let's say we write it down. So let's say we have a system contains a very large number n of particles. So a system has a very large number of particles, which we are denoting by n, each of which can be in any of our energy levels with corresponding energies E sub I, where I can go from 1 2 3 up to R. Okay, the number of particles in the ith level is given by n sub I. That means it's n1, n2, n3, so on, for different energy levels, and the total energy of the system is a constant given by E. Okay, so that's the total energy of the system. So the problem that you want to solve is find the distribution of particles amongst the energy levels that maximizes is the expression P equals n factorial divided by n1 factorial, n2 factorial, n3 factorial, nr factorial. Okay, so if you see this, what we want is we want to find out what should be the particle distribution, or let's say what is the distribution of particles among the various energy levels such that this expression is maximized. Okay, so and if you see, this is P. What is P denoting? It is telling us the number of ways in which we can arrange n particles in I, or let's say R energy levels. Okay, so that's the expression for the total number of ways that we can do it. And if you want to maximize this, that maximization brings us to the idea of the most probable distribution that we will see in the parallel lecture videos. Okay, so we want to pose this problem as an optimization problem. Okay, so let's write that. So we want to maximize this expression given what are the constraints. So subject to the constraints, what are the constraints that subject to the constraint that the number of particles and the total energy remains constant, and the total energy remains constant. Energy remains constant. So what we essentially imply is we want to preserve mass conservation and energy conservation. So we want to deal with an isolated system basically. Okay, so we can write the constraint in this way. So what we want is, let's write G equals n minus sum over n I is equal to 1 to r, and that condition needs to be true. That's one constraint. And the another constraint is H equals E minus sum over I is equal to 1 to r Ni E sub I equals 0. So this is the mass conservation and this is the energy conservation basically. Those are the two constraints. Okay, so what we need to do, so we got our optimization problem. We have to maximize this expression P subject to these two constraints. Okay, so here you see where we will be able to apply the method of Lagrange multipliers to find out the most probable distribution. Okay, so let's observe one thing. So if you want to maximize P, what we want to do is basically minimize the denominator. Okay, so, and minimizing the denominator is same as minimizing the logarithm of the denominator. And why we want to do the logarithm? Because we saw in the previous segment about we want to use Stirling's approximation because we want to use calculus, correct? That means we want to convert these discrete objects into a continuous function. Okay, so there comes why we take logarithm. Okay, so we want to maximize P. So maximize P is equivalent to minimizing the denominator or the logarithm of the denominator, okay, so that's the denominator, that's the general ideas. Okay, so what we need to do is we want to find, so we cast this problem P rather as a maximization problem as a minimization problem. Okay, because we want to minimize the denominator basically. So the function that we are trying to minimize is f is log of n1 factorial, n2 factorial, n3 factorial dot n sub r factorial, and using the properties of logarithm where the multiplicative log of the product of quantities could be converted into additive quantities, you can write this as n1 factorial plus log of n2 factorial plus log of n3 factorial plus dot log of nr factorials. Okay, and now given that we are dealing with very large number of particles, with very large number of particles, that means any arbitrary n sub I is much larger than 1, and hence we can use the Stirling's approximation. Okay, so what we will do is here we will use the Stirling's approximation. Okay, so what does Stirling approximation say? So it says that we can write the log of the factorial of n is approximately equal to n log n minus n. If we use this expression for each of the individual terms for n1, n2, and n3, our function becomes f equals n1 log n1 plus n2 log n2 plus n3 log n3 plus dot nr log nr minus n1 plus n2 plus n3 plus dot nr. So that's our function which we want to minimize subject to the constraints of fixed number of particles n and a fixed total energy E. Okay, so we can write this function f in terms of a summation notation. So where we can write this as n sub I log n sub I, where I is the running index that runs over I equals 1 to R minus, and this is basically the total number of particles, so that's basically n. Okay, so that's the function that we are trying to optimize. Okay, so this f, that means we have to minimize f subject to g equals 0 and h equals 0, where remember what was g and h? G and h was given by these two constraints, so the particle conservation or mass conservation and energy conservation basically. Okay, so now we will cast this problem basically. So we have two constraints, as you can see, and we have, you see, r, basically this function. So you can see there are r, you can minimize with respect to r variables basically. Okay, so let us write all the constraint equations. So it will become partial f partial n1 with respect to n1. So if we vary just n1 plus first Lagrange multiply lambda times partial g partial n1 plus mu partial h partial n1 equals 0. So that's the first equation. Like that we can write partial f partial n2 plus lambda partial g partial n2 plus mu partial h partial n2 equals 0. Okay, and this we can write for all of the r states, energy states. Partial f partial nr plus lambda partial g partial nr plus mu partial h partial nr equals 0. Okay, if you see, there is a common pattern among all these constraint equations, so we can write a general version of these constraints. So we can write this as partial f partial n sub k plus lambda times partial g partial n sub k plus mu times partial h partial n sub k equals 0. Okay, so now if we use the individual values for f, this is what f is, and g and h, let's compute each of these derivatives. So let's compute partial f partial nk. Okay, so partial f partial nk is partial with respect to nk, and remember what f was. So f is the sum I equals 1 to r n sub I log n sub I minus n. So and remember n1 n2 n3, all those are independent variables. You can vary all this a number of particles in each of the energy states independently. Okay, so the only derivative we are concerned about is the kth derivative basically. Okay. So what this will become is partial with respect to nk of n sub k log n sub k. Okay, and now we can use the product rule of derivatives. So nk as it is, and the derivative of log nk. So this will become the derivative of log nk plus log nk derivative with respect to nk of nk itself. So this will become, this is partial f partial nk. You see what is partial f partial nk? Partial f partial nk is nk, and the derivative of log nk is 1 over nk, and then this becomes log over nk. So this becomes 1 plus log of nk. Okay, so that's partial f partial nk. Okay, and let's figure out now the second term. this partial g partial nk. So let's write what g was. So g was the particle conservation basically. So this was g was n minus sum over I is equal to 1 to r n sub I. So what we want is partial g partial nk. Okay, so if you see this, so this derivative of n, but this is constant, remember, because we are dealing with an isolated system, so the derivative of that is 0. So this will become minus the derivative with respect to nk of the sum I equals 1 to r n sub I, and the only term that will contribute is the kth term. So this will become minus derivative of nk which is minus 1. Okay, and let's write what was h. So h was e minus sum over I is equal to 1 to r e sub I n sub I. That was n sub I e sub I. Okay, and if you write partial h with respect to nk, again, given that we are dealing with an isolated, e is constant, that is 0. So what we have is negative partial with respect to nk sum over I equals 1 to r n sub I e sub I, and the only term that will contribute again is the kth term itself. This is minus partial with respect to nk of n sub k e sub k. So this becomes minus e sub k. Okay, so we have all the derivatives now. Okay, so we have all these derivatives, and now let's combine all these derivatives. So partial f partial nk, that is 1 plus, so that is, write it in a new page. So that is 1 plus log n sub k. That's the first term, partial f partial nk, and plus log n k plus lambda times partial g partial nk, which was minus 1, plus mu times partial h partial nk, which is minus e sub k, okay, and that is was to 0. Okay, that is the general expression that we found out. So if you see, what this becomes is, on simplification, 1 plus log n sub k minus lambda minus mu e sub k equals 0, or we can write this as log of n sub k equals mu e sub k plus lambda minus 1, or n sub k is e to the power mu e sub k plus lambda minus 1, or this could be written in a way c e to the power mu e sub k, where we realize c is e to the power lambda minus 1. Okay, so we found out, so nk, so that is the particle distribution. Number of particles found in the kth energy state will be given by c e to the power mu e sub k. Okay, so that was the thing that we were looking for. Okay, and this distribution is very important in statistical mechanics, and it is so important that this has a name to it basically, and this is known as the Boltzmann distribution. Boltzmann distribution. Okay, and the constants mu and c could be evaluated from the constraints that sum over I is equal to 1 to r, n sub k is n, and if we use it using this nk, this will become sum over k equals 1 to r c e mu e sub k that is equal to n. And similarly for the energy, sum over k equals 1 to r e sub k e mu e sub k equals the total. So based on these two constraints, the constants could be figured out, but this was the expression that we were looking for, the distribution of particles basically. And you see how we got it. This came from the natural idea of function optimization problem subjected to constraints. Okay, so we wanted to remember what we did. We wanted to maximize this term p subjected to the constraint of a given number of particles and a given total energy. And how we did it? We did it by, so we dealt with the logic that if we want to maximize p, we want to minimize its denominator, and if we want to minimize its denominator, that is same as minimizing the logarithm of the denominator. And so this was the function that we started with, and we took logarithm for a reason, because we wanted to convert the factorial functions to continuous smooth functions using the Stirling's approximation. And that's what we did. We converted f using the Stirling's approximation. This was f, and then we had the constraints g and h, and based on the constraints we wrote the optimization problem using the Lagrange multipliers lambda and mu, and based on that we were able to figure out the particle distribution for the kth energy state, and the constants, the Lagrange multipliers themselves, could be figured out from the constraints themselves. Okay, so this was when we were able to show how the Boltzmann distribution is a result of an optimization problem basically. So this is related to finding out the most probable number of ways of arranging n particles in, let's say, r number of energy states, and the best way to do it, and the equilibrium particle distribution is given by the Boltzmann distribution, and that's what we derived here. Okay, so this was the Boltzmann distribution. So that's for this segment. Thank you.